Hey guys, welcome. Yeah, so example to here with its own pair of differential equations, and this will be our last example because if you watch examples 0, 1, and 2, that'll give you a very, very complete understanding of exact differential equations. Now, if you only had time for either example 1 or example 0, then I recommend that you watch example 0. But in this video, I assume that you've watched both example 0 and example 1. So I'm not going to repeat some of the more basic details that I talked about in those videos. Alright, with that said, let's get started here. And it's pretty clear in A that this is, and I want to write in red. So in A, it's pretty clear that this is M, and this here is N. And notice that this time M and N are both functions of T and Y, both in A and in B. Yeah? Okay, alright. Now, let's write in A, M of Ty, sorry guys, Ty over here, and distributing this Y so that it's easier to take the partial derivative with respect to Y of M. So we distribute that Y, right? And we write that M is 1/2 Y squared, and then minus 2Y, and then e to the t, right? Okay, cool. And then n of t comma y needs no modification, y minus e to the t, right? Okay, cool. Now, what we need to check is if the partial with respect to y of m, so my, which is equal to y minus 2e to the t, is in turn equal to nt in this case, and nt is going to be negative e to the t. So the answer is no, my is not equal to nt. And since here we have that our equation is in terms of t and y, this would be like my is equal to nt instead of nx, obviously. And we see that my is not equal to nt, so A is not exact. And that's how it worked out in example 1. And in example 1, B was exact. So is that how it's going to turn out here? Maybe, I don't know. You'll have to wait and see. Okay, cool. So let's get started with B then, right? And so in B, what do we have? We have in B that this here is M and this here is N, right? Okay, cool. So again, let's write M and N more clearly. So we have M of t comma y, and it is equal to, we can write it a bit more succinctly, and that's by distributing that sec t. So we get y sec squared t, and then, I don't know about succinct anymore, plus sec t tan t, but it'll definitely make it easier to take the derivative and recognize a couple of other things to come later. Anyway, that's that. And then and I'll actually keep it higher up because we need it. And then later. And then n of t comma y is equal to clearly 2y and then plus tan t, right? Okay. So now is my equal to nt? Well, my, partial with respect to y of m, is clearly equal to sec squared t. This is 0, right? When we take the partial with respect to y, that's 0. And this part, that goes away, and that constant stays, which is sec squared t. Yeah, okay, cool. And then when we do nt, then we make this 0, right? It's a constant. And we're doing partial with respect to t. And then this is going to turn to secant squared t. Yeah, so it worked out just like example 1, which is B is exact and A is not. And A is jealous. Okay, so my is equal to nt. And that means now that, lucky for us, we have to solve B. Yeah? Okay, cool. Now, to solve, we made a very important observation in example 0 that we recited in example 1, and that was this, which is that the way we get to M is by taking our solution phi of xy and taking the partial with respect to x of phi, and this time it's going to have to be t, right? So technically I should write the partial with respect to x of phi. In fact, I'll do that, and since we're just keeping in mind that everything here with an x is a t. We'll do that with this, yeah? Okay, all right, that's how we get to m, taking the partial with respect to x of phi. Now, watch example 0 to fully understand that. And the way we get to n is we take the partial with respect to y of phi. Probably guessed that. Okay, cool. So I'm telling you this because the way we get to our solution phi is either by integrating m with respect to x, and by that I mean t in this particular case, or by integrating n with respect to y. And since I integrated m in example 1, I'm going to integrate n in this example 2 for variety's sake. So n dy is what we do then, and that'd read here 2y plus tan t, and then dy, right? Okay, so that's gonna say that we've got y squared, and then it's gonna be plus tan t times y. So let me make it very clear that we're multiplying all of tan t by y. Yeah, okay. First one was big, the second one was thin. Okay, anyway, that, and then plus some function h of x, and then plus some numerical constant k. Now the plus k we understand because it's typical that we write plus a constant every time we integrate, right? But what is this business? Well, because we integrated m in example 1, we had to write h of y in example 1, and I sufficiently explained why we had to do that in example 1, why we had to write h of y when we integrated m with respect to x. So technically, I should not explain here, and by the way, in our case here, it's h of t, right? I just saw that, but yeah. The reason why we have to do it, so I'll explain, even though I explained in example 1, I'll explain again. The reason why we have to do this is because this here is supposed to be phi, right? And phi is a function of t and y this time, as opposed to x and y, as it is often done. But yeah, you get that. And since this here is phi plus some constant k, we know that the way we get to n from phi is by taking the partial with respect to y of phi. So this is phi, and the way we get to n is by taking the partial with respect to y of phi. That's how we get to n. But then when we take the partial with respect to y of this phi here, anything that's strictly a function of t is going to be treated like a constant, so it's going to disappear when we go to n. So when we go backwards from n to phi, we need to keep in mind that such things might have disappeared. Yeah? Okay, that's why we need this h of t here. Got it. But before we say we're done, we need to figure out what this h of t is. And this k here, we're not going to be able to figure out because we don't have an initial condition. But the h of t we can figure out, and we need to figure out before we say we're done. Now, we just said that this is phi, so figuring out h is pretty nice and straightforward. And that's because we know that this is phi. We know that phi of x has to equal m. And in this particular case, we mean phi not of x sub x, but sub t. And by that, we mean the partial with respect to t of phi. Slate, I can't talk. Okay. So yeah, we know normally, in case like I kind of confused you just now, I don't think I did, but just insurance. So we know that this is true, right? So since we're using t instead of x, we know that this must be true. But wait, we know what m is, right? We know m is, in this case, and I said I would save it maybe and I didn't, but m is, in this case, we know y times secant squared. This is why I wanted to save it, because I didn't want to rewrite it here. But yeah, it's this plus sec t tan t, right? This is m. And I know that because we said this is m right there, right? It's in our equation. But we also know that we can get to m by taking the partial with respect to t of phi. And we have phi supposedly right here. So let's take the partial with respect to t of phi. And that's going to be also m. And that's going to say we've got this is going to be 0 since we're doing the partial with respect to t. And in this part, we're going to get secant squared t times y. So I'll write it as y times secant squared t, so that it's easy to compare. And then we'll have plus h prime of t. And I said the magic word just now, a little bit ago, which is compare. So comparing this here and this here, it's pretty obvious that h prime of t, and that was supposed to be red, so h prime of t is going to have to be secant t plus tan t. So if that's the case, if h prime of t is equal to sec t times tan t, then it's pretty clear that h of t, where do I write it? Right here, why not? It's pretty clear, and that's an h, by the way. My h and l or whatever look alike. So h of t will have to be equal to sec t, right? Okay, so there we are. We just we said that all we had left to do was determine. I know, right? Like my writing, but all we had left to do was determine what h of t is, and we just did. So just replace this h of t right there with sec t, and then we are done. Yeah. Okay, cool. All right, I hope you enjoyed this video series, and I hope you learned a lot, and a lot more differential equations videos to come. Yeah? Okay, all right, keep watching. Take care.